Hello and welcome to Selection with Sathi. Today we are going to explore common growth rates, the fundamental language we use to describe how fast algorithms run. Whether you are preparing for GATE CSE, placement interviews, or competitive programming, understanding these growth rates is non-negotiable. We will walk through the complete hierarchy from O of 1 all the way to O of n factorial, serial operation counts for different input sizes, and build your intuition for which algorithms are practical and which are not. Let's get started. Let us begin with the complete growth rate hierarchy. Look at the formula on screen. This is the full ordering from slowest to fastest growing. It starts with 1, which is constant, then log n square root of log n log squared n square root of n, then n log n squared n cubed. 2 to the n. 4 to the n factorial, and finally 2 to the 2 to the n. Now for GATE MCQs, you don't need the full list. Memorize this simplified version: O of 1, O of log n, O of root n, O of n log n, O of n squared, O of 2 to the n, O of n factorial. Everything up to n to the k, for some constant k, is called polynomial time, and these problems are considered tractable. Anything exponential or beyond is intractable, and that's where NP-complete problems live. Let us look at the two fastest growth rates, O of 1 and O of log n. O of 1 means constant time. Look at the code on the left. Accessing an array element by index takes O of 1. A hash table lookup is also O of 1 on average. Pushing and popping from a stack. O of 1. But here's a common misconception. O of 1 does not mean exactly one operation. It means the number of operations stays the same regardless of how large n gets. Even if it takes 100 steps every time, it's still O of 1 because it doesn't grow with n. Now O of log n is logarithmic time. The classic example is binary search, shown in the code. Each iteration cuts the search space in half. This halving pattern is the signature of O of log n. Whenever you see a loop like while n greater than 0, n equals n divided by 2. That's O of log n. Next up, O of n and O of n log n. O of n means linear time. Your algorithm looks at each element exactly once or a constant number of times. Look at the find max function on screen. It traverses the entire array once, comparing each element. That's O of n, linear search, counting elements, computing a sum, all O of n. There is an important rule here. If your problem requires looking at every element at least once, your algorithm cannot be faster than O of n. Now O of n log n is what we call linearithmic time. This is the sweet spot for sorting algorithms. Merge sort, heap sort, and Python's built-in tim sort all run in O of n log n. And here's the key insight for GATE. O of n log n is the theoretical lower bound for comparison-based sorting. You mathematically cannot sort faster using only comparisons. Now let's talk about O of n squared and O of n cubed. O of n squared comes from two nested loops. Look at bubble sort on the left. The outer loop runs n times. The inner loop runs up to n minus 1 minus I times. Total is roughly n squared over 2, which simplifies to O of n squared. Selection sort and insertion sort are also O of n squared in the worst case. O of n cubed appears in 3 nested loops. Look at the matrix multiplication code. 3 loops of size n each give n cubed operations. Floyd-Warshall's all pairs shortest path is another O of n cubed algorithm. Now for practical limits. O of n squared is manageable for n up to about 10,000. O of n cubed only for n up to about 500. Most brute force solutions array O of n squared or O of n cubed, and your job in competitive programming is to optimize them down. Finally, the scary ones, O of 2 to the n and O of n factorial. O of 2 to the n means generating all subsets. Look at the code. We iterate through all 2 to the n bit masks, and for each mask we check which elements are included. A set of 20 elements has over a million subsets. A set of 30 elements, over a billion. Naive recursive Fibonacci is also O of 2 to the n. O of n factorial is even worse, that's generating all permutations. Brute force traveling salesman checks all n factorial routes. For n equals 12, that's 479 million permutations, barely feasible. For n equals 15, it's over a trillion, completely impractical. These are NP problems. To handle them for larger inputs, you need dynamic programming, greedy algorithms, or approximation techniques.
Let us put real numbers to these growth rates. Look at the operation count table on screen. For n equals 10, O of 1 gives 1 operation. O of log n gives 3. O of n gives 10. O of n log n gives 33. O of n squared gives 100. And O of 2 to the n gives 1024. All manageable. Now for n equals 100. O of n squared jumps to 10,000. And O of 2 to the n becomes 10 to the power 30. That's a number with 30 zeros. For n equals 1000. O of n squared is 1 million, still okay, but 2 to the 1000 is 10 to the power 301. No computer can handle that. For n equals 10,000. O of n squared is 100 million, which takes a few seconds. O of n log n? Only 133,000. This table is why algorithm choice matters. The difference between polynomial and exponential is the difference between feasible and impossible. Let's trace binary search on a sorted array of 1024 elements. The key question is, how many comparisons do we need in the worst case? Step 1. We check the middle element. Now 512 elements remain. Step 2. Check the middle again. 256 remain. Step 3. 128 remain. Step 4. 64. Step 5. 32. Step 6. 16. Step 7. 8. Step 8. 4. Step 9. 2. Step 10. 1. After just 10 comparisons, we have either found our target or confirmed it's not there. 10 comparisons out of 1024 elements. The math is simple. Log base 2 of 1024 equals 10. For a million elements, that's only 20 comparisons. For a billion elements, only 30 comparisons. That's the extraordinary power of logarithmic growth. Now let's compare O of n squared versus O of n log n with a concrete example. Take n equals 10,000 and compare bubble sort against merge sort. Bubble sort with O of n squared does 10,000 squared equals 100 million operations. Merge sort with O of n log n does 10,000 times log 10,000. That's 10,000 times about 13.3, which gives us roughly 133,000 operations. The ratio is staggering. Bubble sort does 750 times more work than merge sort. In real time, assuming a billion operations per second, bubble sort takes about a tenth of a second, while merge sort finishes in 0.000133 seconds. At this scale, the difference seems small, but increase n to a million and bubble sort takes 1,000 seconds while merge sort takes 20 seconds. This is exactly why we study growth rates. Let's see exponential growth in action with subset generation. For n equals 10, we get to the 10 equals 1024 subsets. A modern computer generates all of them in under a millisecond. No problem. For n equals 20, we get to the 20, which is about 1 million subsets. That takes about 1 second. Still manageable. For n equals 25, to the 25 is about 33 million. This takes around 30 seconds, getting uncomfortable. For n equals 30, to the 30 is about 1 billion subsets. This takes minutes and will often cause a time limit exceeded in contests. Notice the pattern. Every time n increases by just 1, the work doubles. Going from n equals 25 to n equals 30 multiplied the work by 32 times. This is why exponential algorithms need to be replaced with dynamic programming or other optimization techniques whenever possible.
Let me give you 4 essential tips for exams. Tip 1. Memorize the growth rate hierarchy. O of 1, O of log n, O of root n, O of n, O of n log n, O of n squared, O of 2 to the n, O of n factorial. This ordering appears directly in GATE MCQs asking you to rank functions. Tip 2. O of n log n is the theoretical lower bound for comparison-based sorting. You cannot sort faster than n log n using only comparisons. Counting sort and radix sort beat this, but they use the structure of the data, not comparisons. Tip 3. If a loop halves its variable each iteration, like I equals I divided by 2, then it runs O of log n times. This is the binary search pattern. Tip 4. If your algorithm is exponential, O of 2 to the n, you need dynamic programming to bring it down to polynomial. The classic example is Fibonacci. Naive recursion is O of 2 to the n, but DP makes it O of n. That was common growth rates explained with code, tables, and real numbers. We covered the full hierarchy from constant to factorial, so operation counts explode for exponential growth, and learned when each complexity class is practical. For more concept videos like this, download the Selection with Sathi app. Like and subscribe. Thank you.